Hello, ladies and gentlemen, and French fries and dogs. How are you doing, everyone? This is that magical time of day when we do another Numpy tutorial. And last tutorial, I promised we were going to set up a math playground with slides and merry-go-rounds and kids eating ice cream and dripping it all over their feet and then climbing in my car and getting it all sticky. It'll be fun. So here's what we do. We want to be able to interact with our math in real time, so we're going to use two different kinds of handlers. And let's talk about those handlers. So inside your interactive Python console, we're going to show you what these handlers are and how you access them and talk about them. So if you already know all this stuff, you can skip ahead a little bit, but you might pick up something anyway. Let's just look at the handlers. So we have bpy.app.handlers .scene update pre. Now this is going to be treated like a list, basically, and you'll see that it is a list, and currently there's nothing in that list, but we can append it. To append that list, we need to create a function, and we need to just append it like you would append any list with like .append. So let's pretend like I didn't write any of this yet, and I didn't script the last tutorial and have to start over. And let's show you an example of how this works. So this code is the leftover code from the previous tutorials. We will use it, so I'm leaving it there for now. And I'm going to create a function that I want to run inside my handler. And I'm going to call my function something really unique and special, so it doesn't get confused with anything else, and it makes perfect sense. I'm going to call it do, because it's going to do stuff. And what's it going to do? It's going to print something, like something, because I'm feeling literal. Now, I can't actually do like bpy.app.handlers.scene update pre append do, because it's asking for a function, and this is just the way the Blender's set up. It's just a convention the way they did it. It needs a function that has one argument. So I could put, like, everybody puts scene in here. I don't know why. I don't think it matters what you put in there. You could put, you know, puppy in there. And if I do this, then I'm doing something sort of dangerous, because scene handlers run all the time continuously, and if you're doing something like writing to a dictionary and you have a scene handler that's writing to a dictionary, well, it's just going to keep adding, depending on your code. It could just keep adding to your dictionary until your RAM is full, and you could crash Blender, and you could actually crash your whole entire computer by like maxing out the RAM. Your computer does nothing, and you'd have to like hold down the restart button or something. So make sure you save your work before you get into playing with handlers. Now I've got this tiny little thing here. It's just this handler that's taking the function do, it's putting it in a scene handler, and over here is my readout. Now watch what happens when I append this handler. It prints something like 1,000,000 times. So this is just going to be running continuously. It's still printing over here, you can't tell, but yeah, it's doing that. So now if I do over here in my console and I say, let's check the length of this list, it's now 1. And it has, inside this list here, it has the function do, which is what I named my function up here. And so we can just delete that by index and get rid of it. So delete, and we're going to delete just the last one that I added, which is -1. And now it's actually stopped printing over here. So, like if I did, you know, print, you can see it's no longer printing. So we just got rid of it. It's no longer doing that thing. It would make more sense if I did something like print count. So we're going to print count. And we're going to say count is a global variable. Count equals 0. And we want to talk to that global variable outside of our function, so we're going to make it global here. And we're going to say count plus equals 1. And now we're going to put it inside of our scene handler, and now watch what happens. Now these numbers are just counting like crazy, and it's running all the time, and there's all kinds of things that trigger scene handlers in Blender. If you have this function inside your scene handlers, it's just going to run continuously, so keep that in mind. And you know, it slows down a little bit when you're doing other stuff. If you have a bunch of handlers in here, like if you just kept appending this over and over again, I'm putting one handler after another in here, then I've got a ton of handlers in here, a whole bunch of functions. See this list of handlers? It's the same function do over and over and over again. And I would have to go in and delete them all to get rid of it, to make it stop doing that. And I'm just going to delete it until there's no more left, because I just added it a million times, and yeah, now there's none left, and it stopped counting over here. Well, we don't necessarily want to just delete all of the scene handlers, because there are some add-ons people use that use scene handlers. Like the modeling cloth add-on that I showed off recently uses a scene handler. You don't want to delete that if you're trying to do something with it. Or I think the measure it add-on, the one that lets me see these indices, I think it uses a persistent handler, so it's a different kind of thing. But the point is, there's some handlers, some add-ons that use handlers, so you don't want to just randomly delete them. Well, it is a little bit tricky to figure out how to delete just my handler. So what I'm going to do is make a loop here for, let's see, what is it? I in bpy.app.handlers.scene update pre. Hopefully I spelled everything right. App.handlers. If I dot, and we're going to do name this way, name, because it's not a typical attribute. We use the double underscores. I think it's in a constructor. If I dot name equals, and now we're going to do, my function is currently called do, then if this happens, if it's named do, then you have to do, you can't just do delete this way. Blender doesn't respect this kind of operation. It does when you do it by index, but it doesn't when you try to do it inside of a loop here. I don't honestly know why. So what you do is you do Blender's built-in way for removing it. You do bpy.app.handlers.scene update pre .remove, and use the function built to remove it. And then just put an I. And that will prevent you from adding this function over and over and over again. Now, if you had like 100 scene update handlers and you tried to delete them all this way, like if you had, you know, 1,000,000 copies of do in here, you tried to delete them in a loop, well, you're deleting items out of a list while you're iterating through the list, and it's not going to work. It's going to delete some of them and it's going to exit early, and it's just going to be weird. So as long as we're managing our code carefully and we're only putting the handler in there one time, it's going to, if the handler's not in there, it's just going to do nothing. If the handler's in there one time, it's going to delete it that one time, and then it's just going to exit the loop. So this is fine as long as we're only deleting it once. You wouldn't want to do this for, like, if you had that handler in there a dozen times. It just won't work. So let me just show you what this does here. Let's disable this code for a second, and we're going to run this thing, and it's adding our handler now, so it's counting up all these numbers. And now we're going to disable adding the handler, so we're no longer adding it. And we're going to run the code again, and it's going to find that handler and delete it. And if there's other handlers in there from other functions, it's going to ignore those because it's only looking for one's name to do. So this is the way that I prefer to remove my handlers and manage my handlers. And we're doing it this way where we remove the handler and then we add the handler because we're doing some experimentation, and this is the way we want to do it. So set up your code to look like this, and you'll be able to follow along with my tutorial. And then we have another limitation here, and that is that the function that goes inside of a handler can only take one argument, and it doesn't matter what name you put in here. I don't even know what this is. I think what it does is this is the scene object, and it has access to attributes that are like custom Blender properties. So you could do, you know, puppy.myProperty if you've created properties and stuff like that. I don't generally do it that way because I haven't taken the time to figure out exactly what this is for. You can do that if you'd want to and post comments in the videos. That would be great. For now, the limitation is you can only put one argument in here. So I generally don't do it this way. I generally create two functions. So I have my do function, and, you know, like if you tried to put, you know, puppy and then OB, and you tried to append it, you just get an error message. It actually dropped it into the scene, but it's running with an error, so that's really annoying. And it's because of those two arguments. It doesn't understand what it's doing. There may be a way around that I don't know, but I don't care. I just do two functions. We need to get rid of it now. So we're just gonna hopefully get rid of it. And then print. Okay, yeah, so we got rid of it. It's not doing this error thing over and over again. And we're gonna get rid of this argument here, and we're gonna build a new function. We're going to do myHandler. myHandler, and we're going to put what we should put in there, which is scene. And we're going to, inside that handler, do one thing. We're going to call my do function. Somebody who knows Python better than I do is probably going to be like, dude, you don't have to do it. You don't have to build do functions. That's great. Post them in the comments. And I will believe you, and I will learn from you. Like, hopefully you're learning from me. Now, my handler object, or function, I guess it's an object, is going to go in here instead of do. And the function that I'm looking for to delete is going to be myHandler instead of do also. And now I'm free to put as many arguments as I want into my do function, and my, like for example, I could get rid of this global variable because global variables are evil and you don't want to use them. But it wouldn't count correctly, so I would need to still declare it outside of a thing, and I don't know, I can't think of how to do that right now. But I don't care, because I'm not worried about that. I'm going to put, let's see, here's my object, and we're going to start playing with math over here, so I actually need to do something with these handlers that I've been talking about. Before I do, though, I wanted to show you not just the scene update handler, but the frame change handler and how that's different. And the frame change handler is actually safer, so you might want to just start with that because you can turn it off and on easily. So I've got my windows down here. There's this little corner thing. You can pull it up and make another one. And then you want to set this to a timeline. I'm just going to pull that down because I just wanted the timeline, and I'm going to middle click here. I can, by middle mouse wheel clicking, I can move this around. Here's my pause and play. This lets me start Blender's frame handler, so it's like playing animation. And we want to put a handler into the frames so that every time a frame changes, it runs our function. And that's really easy to do. You do it just like you did with the scene update handler. You do frame change here. Frame change. PRE. It could be post, it could be PRE. They do basically the same thing. One does a bunch of calculations, or does your function before it runs other calculations. One does your function after it runs other calculations. For all of the tutorial, or for all of the code that I've written, I've never noticed a difference. There's probably a difference. If somebody wants to post about the difference, that'd be great. Explain it to me, because I don't completely understand it. For now, we're using PRE, and let's do something with this frame change handler. So I'm going to go back to my do function, and I'm going to make, just because I forgot to do this part, and count plus equals 1, and print count. And then we're going to put that inside of our frame change handler. So what's happening here is my handler with one argument is going into the frame change handler list, and my handler is running my do function. So if I did this right, then when I hit play down here, it's going to start adding my numbers. So you'll notice my numbers are counting up while this thing is running, while the animation is running. Seems to be lagging for some reason, I'm not sure why. Now, if I run this backwards, let's see, play backwards, you'll notice that numbers are still going up because it doesn't care which direction it's running. It just cares that it has changed frames. I'm on frame 200, my number's at 387. If I type in, 5,000, then my number's at 388. It doesn't care how many frames have changed. All it's doing is it's running this function anytime we're on a new frame. Backwards, forwards, a million frames ahead, a million frames behind, it doesn't care. Keep that in mind so you don't get confused. If you're expecting something to move in a linear direction and it doesn't when you go backwards or something like that, it's just running your function every time a frame changes. Okay, we're going to just use that for now, and if I did this again, if I run the script again, well, now my handler's in there twice, so it's running two separate handlers, and we don't want that. We want to clean that up. So we actually need to go down here and delete it, since I just added an extra one. We will do this in our script here in a second. So frame change PRE 0, delete, and there's another one in there, because there's two, and now if we try to do it again, there aren't any more, so it gives us an error. And now if I run, if I play, it doesn't do anything, and that's what we want. So I'm checking for scene update handlers here, and I'm deleting them, but we're not checking for the frame change handler, so we need to copy this code. And we're going to just change this from scene update PRE to frame change PRE. I think I got that right. Yeah. Now we're going to update it here, and I believe we're good to go. Now it's checking for scene update handlers named myHandler, and it's checking for frame change handlers named myHandler, and it's going to delete either one if it finds it. So let's go ahead and add both of them, and I'll just not delete. Let's add both of them, and I'll show you. Now, if I hit play, it's going to start my frame change handler on top of my scene update handler, and they're trying to compete with each other, so you hardly even see the frame change one. That's this little tiny blip that's probably not even going to show up on the video. I want to get rid of those now, so it stops counting, and it got rid of both of them, so yeah. So now we're doing cleanup for both of these handlers depending on which one we want to use. And we're going to start with the frame change handler. Now we're going to do something interesting with this handler. So we've essentially now built our math playground where we can start doing fun stuff. And the fun stuff we're going to do is we're going to run some calculations inside of our do function that relate to our geometry over here. So we could, for example, this isn't going to be very exciting or fun or cool or anything, but it'll be something. We're going to take CO, and we're going to take CO0, and we're going to print it. So we don't need count anymore. We're going to get rid of that. That was just for show. We're going to print CO0. Now run this, and I'm dropping it in the frame change handler, so now when I play the animation, it's going to print the location of that point. If we grab this and move it, it changes, theoretically. And it's not changing. So give me just a second here and I'll figure out, why didn't that change? What did we do wrong here? CO equals blah 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 for each set, Is it because we're setting the CO? Yeah, it's because we're setting it back. In fact, what is it doing? Oh, no, it's working. Oh, I know why. It's because we're not actually getting the coordinates inside of our handler. We're getting the coordinates outside of our handler, so this isn't getting updated. So that's another detail that's important. OB equals bpy.context.object, that's fine. That's a reference to the active object in the scene, and you can leave that outside your handler if you want. But CO equals get CO OB needs to go in here. And this actually needs to go in here if we want it to update in real time while the animation is playing. So that's something that's tripped me up a lot of times when I was trying to do projects and I was like, why isn't it working? Make sure you update what you need to update inside your scene. Okay, now theoretically, if this animation is running and we move this, yeah, see now it's changing in real time down here. It doesn't change it while you're in edit mode because it doesn't update it until after you pop out of edit mode. So we want to make it so that you can work with this outside of edit mode and still see the updates. So to do that, first of all, I'm going to stop this animation. We could do something like, we could add a hook. So down here in your properties, you can go to the modifiers tab and you can add a hook modifier, and then you can, let's see, set it to an object and all that stuff, and that's fine. You can also just do Control plus H, and now I have a hook object. And now this vertex is hooked to this guy, and that vertex is moving around. Now, we're outside of edit mode, we're moving this vertex around. You would think that, and actually is this vertex 0? No, it's vertex 2. We probably don't want that, so we're going to delete that. And we're going to add it to vertex 0. Control H, hook to new object. You would think that since, you know, everything seems to be right, you would see updates to the location of this vertex. Well, you don't, because if you access this vertex data through the Python API, it's going to give you the mesh before the modifier effects are added. If you want to get the mesh after the modifier effects are added, you have to do a little bit of futzing around with some other stuff. So I've got this other function that I've written, and I'll just write it for you really quick so you can see how this works. We're going to do a new function. Oops. We're going to do get, and I'm just going to call it Proxy because it's like another version of the mesh. Proxy CO and OB. So this is the same here, provided you're not using a subsurface modifier or something that changes the vertex count. This is the same here. Length ob.data.vertices. This is the same here, except that rather than getting the coordinates of this object, we actually want to get the coordinates of the object as if the modifiers were applied to it. So for that, we're going to create a mesh. And let's see. How does this work? We're going to say mesh. Let's see. ME equals ob dot to mesh. Is that right? Yeah, ob.toMesh. And we have to put in the scene, which in this case is bpy.context.scene. And we want to, I can't remember what this argument is. Let's see, it doesn't matter. Put in true as the next one, and then preview. We're going to use preview. And preview is a setting down here. So you've got this modifier down here on your object. This is the properties window, by the way. Properties. And this is the modifier tab in properties window. And this is the list of modifiers that are on there. We've got this hook modifier on here, which is this thing, and it's hooked to this empty. These are the settings, so like if I turn preview off, you no longer see that. Let's go back to where before we moved that. Alright, so this is the preview setting, this is render settings, etc. When I say preview, I'm saying use the setting over here. We want to, if this was turned off, then preview would do nothing. If it's turned on, then preview will take this setting and it will apply the modifier to it. You could set this to render if you wanted, right here instead of preview, and it will respect whether this is on or off instead of whether this is on or off. Generally, preview works, so just use preview. And now, instead of the object's data, the object mesh, we're going to use this. This is a version of the mesh with the modifiers applied. So data gets replaced with ME. So we go all the way to there and we do me.vertices. And then co.shape equals that, etc. Now every time you do this, you're creating a duplicate. So we want to do bpy.data.meshes.remove me, because we don't need them after we've gotten the coordinates. So let me just show you. We append our handler like we did before. We're not using this function yet, so nothing has actually changed as far as how this works. We run this, we hit play, and it's printing out our coordinates, and nothing is happening. It's still taking the same coordinates. So if we swap that out for this one that takes the coordinates with the modifiers applied, so this is no longer oh, and I actually undid my changes when I did undo a second ago. I didn't want to do that. Wait, did I? CO equals get CO object. Oh, no, it's still right. I just didn't need it up here. It's not doing anything. So we're going to do CO equals get Proxy CO, which is the new function that we just created. And if we run this inside of our handler... Okay, so we figured out what's going on here. I had to pause the video for a second. When you have this empty selected, it's a none type object. So when you run this thing with your empty selected, remember we're using bpy.context.object. So I've got this active, I run script, and I hit play, and it throws errors because this does not have data, and we're looking for its data. So if we select this first, so it's our active object, run script, hit play, then it's showing us our vertex coordinates at 0, which is what we want. Now, everything should be working right. You should see an update here, but you don't, because we're not getting the vertex coordinates with modifiers applied. Well, our modifier is being applied to ME, and then we're taking our data off of ME now, and we're making an array based on the data, and we're reshaping it, and we're returning it, but we're also, I forgot to put in the step where we overwrite it. So we need to do me.vertices dot for each get, and then I'm going to do CO and CO, just like we did up here. And now, if we call this function get proxy CO instead of get CO, so down here we're doing get CO, we want to change that to get proxy CO. And then we're printing that out. Theoretically, if I did everything right. Now, well, we have to have this object selected first before we run script. And now when we hit play, we're printing out our coordinates, and this should update, which it does. So now we're seeing the coordinates with the modifiers applied. Now if you use this with like a subdivision surface modifier, in fact, let's just go ahead and do this. I'm going to hit Control 1 and subdivide it. And now I try to do this, it's going to give me, let's see, pause. It'll still work, but things can get funky if you try to set it back, because you can't set the coordinates of the object. You now have a vertex count. Let me just show you. So we're going to print CO. We're also going to print co.shape. Actually, let's not print that. I have this selected. We run this. We hit play. Our shape is 9,3. Well, the shape of our mesh, it actually only has 4 vertices, but subdivided it has 9. So if you tried to write this proxy CO back to the mesh, you're going to end up with an array full of 9 vertices, and you're going to be trying to write it to an object that has 4 vertices, and you're going to get errors. There are ways around that. Basically, if you needed to get the subdivided mesh's coordinates, but you wanted to write it back to the original mesh, you now let's see, there's a couple of different ways you can do it. Basically, you can't work with subdivision modifiers this way. If you wanted to do like a subdivision modifier and like an armature which doesn't change the mesh count, you can go through and you can change the armature modifier to preview true and the subdivision to preview false, get your preview mesh and do it that way. So it takes some workaround. It's just something to think about if you're reading and writing mesh data and you're trying to use modifiers that change the visual vertex count. It gets tricky. I'm going to just turn that off because we don't care about that right this second anyway. So now we've got this cool thing where we're taking the location in real time as the mesh is changing, and I hate this thing that we actually have to keep selecting the object. So I'm just going to say this object is P, and instead of bpy.context.object, we're going to do bpy.data.objects, and we just named it P, so we're just going to put P in here. Now it doesn't care what object we have selected. We can run this bpy.data.objects, and when we hit play, it's going to work correctly. We want to print the CO. We don't care about the shape now. We're going to get rid of that. And yeah, it's moving our stuff around. So this is what we want. Alright, now we're going to talk about something that I just sort of skimmed over in the last tutorial, which is normals. And there's a couple other things I wanted to tell you about normals, and I thought it'd be cool if we could look at that in real time. So remember the normal, you can look at it by going over here, turning it on for the face. That's the panel that pops up when you hit N, or you hit this little plus thing over here. You scroll down to normals and you can turn that on and off. It shows this blue line, and you can change how it appears there. Now to access that normal inside of Blender's Python API, let's do it inside our handler because that's cool. We're going to do OB. Is our OB? Yeah, our OB is global, so we do ob.data.polygons. And there's only one polygon here, so that's polygon 0. And we're going to say nor equals that. And if we print our, we don't care about CO right now, we print our normal, then we run this. Now it's going to be printing that other value all the time. Polygon 0, ob.data.polygon0.normal is not defined. Why not? Line 55, 46, do print normal. Oh, because normal is not defined. I wrote normal, not nor. Let's just do that again then. And there's our normal right there. And you'll see that it's 0, 0, 1. And that's because this is a plane and it's perpendicular to the z-axis. So the normal is going to have 0 x value, 0 y value, and 1 on the z value. And theoretically, if we change this like that, then it's going to change over here also, which it does. It doesn't update until you pop out of edit mode, but it actually changes that. Now, you'll notice that we can control the length of this normal here in the view, and when we pop out of edit mode, it does absolutely nothing to this value because it doesn't care about this blue line. That's just a visual aid. So it has no effect on the normal as far as the math is concerned, calculating the normal and accessing it through the API. Now, remember I said I was going to tell you something more about dot products. Well, this normal, if you get the length of it, right now the length is obviously 1 because it has 0, 0, 1. Its total length is 1 because we've moved 1 unit up on the z-axis. Length of this normal is 1. If we rotate it around to something weird like this, you've got this mix. Well, we want to get the length again. The length is going to be the dot product, the square root of the dot product of the normal with itself. So we could do nor dot dot like we did that one time and put nor in again. But instead of that, I'm going to do what I prefer, which is nor at dot, which is Numpy's syntax for matrix multiplication. Nor at nor gives us the dot. So we're going to be printing the dot product of this normal when we run this and hit play. And when we figure out what my error is this time, ob.data. Oh, I know. I didn't actually convert it to a Numpy array yet, so we need to do that. So nor equals np.array. Now it will print this normal, which, because of floating point errors, doesn't print out as exactly 1, but technically, mathematically speaking, these normals are all unit vectors, and a unit vector means that it has a length of 1. So even though the normal, like if we print the normal again, is this crazy mix of, you know, x, y, and z, its length is essentially 1, barring the floating point errors. You know, 1.00000, whatever is actually mathematically would be 1 if you had perfect precision in computers, which you don't. Think of it as 1. Now, another question about normals. Oh, and just in case you're wondering, I didn't do square root to give you the length. So it should be, you know, np.sqrt, this nor at nor. The square root of the dot product is the length. And it doesn't change, it's still 1. And that's because the square root of 1 is 1. I think I already have Numpy imported. np.sqrt 1. You should know that already anyway. If this was not a unit vector, if its length was something other than 1, to get the length you would obviously have to do the square root. So you should always, if you're getting the length of a vector, do this. And if you wanted to, let's say that you had a vector like, we want, actually let's just get the normals ourselves. So let's talk about normals. A normal is derived from the cross product. So what that means, the two fundamental computations inside of geometry are cross product and dot product. They're the most commonly used things. You can do pretty much everything with dot products and cross products. You can do rotations with them. You can even skip sine and cosine and do rotations with just dot products and cross products. The sine and the cosine are actually derivatives of dot products anyway. So they're just everywhere. So you should know what they do. We've talked a lot about dot products. We haven't talked about cross products. This blue line here is actually the cross product of two vectors. And in this case, it's the cross product of more, but I'll talk about that in a second. So if we wanted to get a line that is perpendicular to, like, let's say that this is an edge segment and that this is an edge segment, and we want to draw a line that's perpendicular to both of those guys. Well, these 3 points, right here, here, and here, make a triangle. So 0, 1, edge segment, 0, 2 edge segment. You can make a triangle. We ignore this one for now because it's just not part of this equation. And these three are a triangle, and here's this plane. Well, if we take this edge segment here and this edge segment here, and we compute the cross product, what we get is the normal. Cross product is a line that is perpendicular to two other lines. So let's just go ahead and do that really quick. You can look up the cross product formula. It does some weird stuff. It swaps around the x and the y, it multiplies this by that, and it adds this to that, and it does some other things. It's a really, really common formula. It's easy to find that formula, but I don't really care because Numpy and most math libraries have a cross product formula, and you can just use that. Let's make this a little bit simpler to think about here. For Blender, what it's doing, in all the math and all your video games and everything, this is a quad, but to compute the normal, it actually computes the normal off of the triangles. And even though this is a quad, it's mathematically is two triangles. So if you do something like you move this, well, it's still a polygon with 4 vertices, but you'll see that the graphics card is actually computing it as if it were two triangles. And it's sort of arbitrary which one it picks, or how it decides to divide this into two triangles. If I hit the J key with these two selected, then I get these two triangles and I get these two normals. You'll notice that for the visual aid that Blender's, where Blender's drawing the normals, it's computing the normal at this triangle here by using the cross product of this edge segment with the cross product of this edge segment. And then it's computing the normal of this triangle here by using the cross product of these two edge segments. And then it is giving us an average of those two normals, and then it's converting it into a unit vector. So Blender just does that for convenience. It computes the mix of the normals of all your polygons. So if you had like an n-gon with 20 vertices, let's just do that. Let's make this another vertex. Well, it's going to take this and divide the whole thing up into a bunch of triangles. It's going to compute the normals of all of those triangles and mix them, and it's going to give you the normal of a single n-gon, and that's what you'll be accessing if you go through the Python API. If you've got a mesh with a bunch of n-gons in it, it's going to be actually a normal that's computed as a mix of all the triangles that make up that n-gon. If you triangulate this, then it's taking, this triangle, and this triangle, and it's mixing the normals of those and giving you this one. Hopefully that makes sense. If we get the normals ourselves, we have to triangulate first before we can get it, or we get stuff that doesn't make any sense. So I was talking about unit vectors. Something else that you will need to know is how the heck would you get a unit vector? Like, what if you had a normal that you derive from cross products and its length was something other than 1? How do you get that? Keep that in mind. I want to show you something else really quick, something I forgot to tell you about dot products. We're currently computing the dot product of our normal. We want to start working with this mesh a little bit more, so we're going to start computing some other stuff. We want to get these two edge segments here at 1, 0 and 2, 0, so that we can do some fun stuff with them. By fun, I mean math, which not everyone might think that's fun, but I sure do. So we don't need that. We can keep that there and just ignore it for now. We're going to do... Now I'm using my Measure It add-on, which allows me to see the vertex locations, so that I know that this is 0, 1, and 2, and 3, and all that. And I'm going to make two vectors from these edge segments. So I'm going to say v1 equals co. We're going to do 1 minus 0 to get ourselves a vector that's pointing along this edge. CO1 minus CO0. Okay, and then we're going to do, I'm hitting Control D to duplicate that line. We're going to do v2 equals CO2 minus CO0. And now we're going to print the dot product of those two. So v1 at v2. Now, you'll notice that these two vectors, 0, 1 and 0, 2, these two edge segments are exactly at a 90-degree angle. They are perpendicular to each other. Well, if you remember in last tutorial, we were able to tell when the dot product was negative by when it passed from being on this side to being on this side. So this dot product of these two edge segments here is either positive or negative, depending on where they're at in relation to each other. And if it's on a plane, then it's which side of the plane it's on. If you don't know what I'm talking about, back up to the previous tutorial and you'll remember. So actually, it makes more sense if I look at it this way. So like if we pretend like this is a plane here, and this normal is either on this side of the plane or this side of the plane. Remember, it switches from positive here to negative here, which means that when it's right on the plane, it's going to be in between a positive number and a negative number. It's going to be at 0. So anytime you take two vectors that are at 90-degree angles to each other, they're perpendicular, their dot product is going to be 0. So I'm computing that right here. Now, if I hit play, I should get a value of, yeah, it's essentially 0. It's, 8 decimal places, so it's, it actually looks like, 0.0000000, whatever, 9 something. And because of floating point errors, it's, not exactly 0, but it's, mathematically, it should be 0 if there weren't such a thing as floating point errors. These are at a 90-degree angle, so they're 0. Now if I move this a tiny bit, like in the positive direction, remember our vectors are both pointing from 0 up, from 0 up. Now if I move this over into the positive direction of that other vector, now this becomes a positive value. If I move it over onto the negative side, then that becomes a negative value. And remember that Blender starts out with a plane that each side is 2 units in length. So if I put this guy, like, let's say we have vertex snapping on. Yeah, if I snap this guy over here to this vertex, now what I'm going to get is two edge segments that are 2 in length. They're 2 units in length each. So I'm going to get the square of that, which is 2 by 2. So now when I pop out of edit mode here to update this, it's going to be 4. So yeah, now our dot product is 4. So their length is 2, but their dot product is 4. If I printed, the square root, np.sqrt of that, and it's going to tell me that it's 2. So, yeah. If I wanted to convert that into a unit vector so that its length was 1, regardless of where it's oriented in space and what the mix of all these other things are, then what I do is I take the... let's see, how do I do that? I take the length and I divide the vector by the length. So, for example, v1 has a length of 2 currently, but if I want to make it into a unit vector, first thing I need to do is find the length of v1. So I do v1 at v1. I take the square root of that, which gives me the length of it. So this should print out as 2, which it does. And now I want to take my original vector, which is v1, and I want to divide it by its length. And that will turn it into a unit vector. So now if I print this, I'm going to get a 3D vector now because I'm using broadcasting here where we're taking each value in v1, dividing it by the square root of its length. So actually, what is v1 right now? Let's print it. Print v1, and don't print this for a second. And v1 is currently, 1.7 to whatever. I take 1.7 divided by the square root of its length, which is 2. So this divided by 2, this divided by 2, and this divided by 2. And now when I print that, I get this 3D vector that is, 1.7 divided by 2 is this, and these are each half of these. 1.39 times 2 is this. 2.79 divided by 2 is this, whatever. 9.5 divided by, etc. This new vector that I've created, I've got this vector and I've divided this vector by its own length. Now if I do the dot product of this new vector, so I'm going to say unit v1, I'll call it unit v1. Actually, I usually just do u v1 when I'm doing this. U is short for unit. If I print unit v1, there's nothing special about it. It's just another 3D vector when you first look at it. So it's just this. I did something wrong here. U underscore v1 equals is what I should be doing. So it's just this other 3D vector. But if I give you the dot product of this, so v1 was just this edge segment. I've divided all of the values, all three values in v1 by the length of v1. The length was derived from the square root of v1's dot product with itself. And now when I print v1 divided by the length of v1, I get this value over here. Now if I do the dot product of this, print uv1 at uv1, this is now a unit vector. So it should give me a dot product of 1 now when I print it. And it does. And I'm printing this still. But so now our dot product of our unit vector is the length 1. So to get that again, the formula for converting any vector to a vector of length 1 is simple. You just take the vector itself, divide each value in the xyz by the length. Vector divided by length. Square root of the dot gives us the length. Divide the vector by the length. Ta-da, here you are. Now, Blender's automatically doing that for all of its normals when you access the normals through the API. So you don't have to do that step. But if you want to get the normals yourself, this is a step that you will do if you want to use normals in the typical way where they're unit. Depending on the math you're doing, you don't always have to convert to unit vectors. And it's cheaper if you don't have to do the square root and division stuff. And most of the formulas that I use, I write them in such a way that I don't have to use unit vectors because it's just extra calculations. It can be simpler to understand your code if you just go ahead and do that extra step. That's one less thing to think about if you've already got that done, but it's also not the best performance depending on what you're doing. Alright, moving on. We need to talk about cross products. So to talk about cross products, let's take this empty here and actually let's get rid of this for just a second. Our hooks, we don't need those right now. And let's see, should we use an empty or should we do something else? I think we should do something else. Let's make an edge segment. So, or, you know what, we could do this too. We're going to turn this into a triangle just for simplicity. And we're going to delete this point. And we're going to connect it to 0. Yeah, I like that. So this is going to be a useful thing. So we're going to use this to show us some information. Okay, we said we're going to talk about cross products here. So let me show you something about a Numpy specific thing with cross products. Down here in the system console, we're going to do np.arrange. We're going to do 3. And it's going to give us that. So we're going to say x equals this. Okay, x is now this vector. If you want to get the cross product through NumPy with x and x, or x and y, or something like that, two 3D vectors, you just do np.cross x and x. Now, x and x are pointing in the exact same direction, so they're actually going to be 0, 0, 0, and that's not very useful. So let's do like y equals x plus 2. Well, they're still pointing in the same direction. Wait, are they? I don't know. Let's find out. np.cross. Oops, we don't need a space there. X comma y. Okay, so they're not pointing in the same direction. So now we've got the cross product is a vector that is perpendicular to the two edge segments. With Numpy, it does its broadcasting in unusual ways. So like if we had an array like x equals np.arrange, actually it does its broadcasting in a perfectly logical way, but it does it in a particular way that you need to be aware of. 12, and then, so x is this, and then x.shape, we want it to be 4, 3, like an array of 4 3D vectors. So now x is this, and then y is still this. If we did np.cross, I believe this works, x comma y, then it takes y, which is 2, 3, 4, and it goes row by row, and it gives us this cross product of x. So we have cross product of 0, 1, 2 with 2, 3, 4, 3, 4, 5 with 2, 3, 4, and so on and so forth. If you wanted to do the cross product of x is now 4 by 3 with x, you do np.cross, you do x comma x. Well, it's going to take every row in x, and it's going to do the cross product of every row in x with every row in x. So it should send us a great big old bunch of zeros if we do this, and it does. So these are all just zeros. So there's different ways that you can broadcast cross products with Numpy. If there's just some way that logically the first value has a shape that's divisible by the second value, then it will broadcast it and it will return you something that is logical depending on the shapes of your arrays. For now, we're actually going to be working with just two vectors that are two 3D vectors, so it's fairly simple. So I want to print the cross product. We don't care about this for now. We don't care about this. And we don't care about this. We're going to print the cross product of v1 and v2. And it's just going to be some 3D vector that doesn't make any sense. Is it two 3D vectors, or are we printing a bunch of stuff here? Oh, we printed v1. We want np.cross. Sorry, forgot that step. v1 and v2. And we get this one 3D vector, which doesn't mean anything yet. So we're going to say cross equals. Oops. Cross equals this. And we're going to set this guy over here at the location of that cross. Now, if we take the location of that cross, it's actually going to put it over here starting at 0, 0, 0. So it's just going to pop way over there. Let's just do that so you can see. So we're going to say CO, and this point here is at 3, so we're going to say CO3 equals cross, and then we're going to do, we're going to write that back to the mesh, and we have to do ob.data.update parentheses, and theoretically that point will jump over, yeah, the object's location is way over here, and so wait, let's apply the location. Let's apply the rotation, let's apply the scale. Okay, now when we hit play, it's going to pop over there to where the cross product would be if this were at 0. So we actually need to add this origin with it. So we take the origin at 0, so that's just CO0. We say cross, CO0 equals cross plus CO, CO3 equals cross plus CO0. Now it should pop over to where it's supposed to go, which is correct. And this is really interesting. You get this line here that is exactly perpendicular to these two edge segments. And I think, let's see, if we add a hook over here, like to this object, while this is running, yeah, because we're updating, it's actually, it's updating twice, so it's moving it around weird. But as we move that edge segment around, our new angle stays perpendicular to those two edge segments. And I should probably fix that. It's annoying to fix. I remember how to do it, I've done it before, but I'm not going to worry about it right now. Point being, we've just gotten our own normal. Now if we want to convert this to a unit normal, first of all, let's go and undo all that weirdness that we just did. And in fact, let's just delete this hook because it's getting in our way. Run this script again and hit play, and now if we move it over here, it stays perpendicular. And if you, as you're moving this around, in fact, let's just delete this edge segment. As you're moving this around, it's changing. It's always going to stay perpendicular. It also, like, let's see, its length happens to be, we're going to set this pivot to center and we're going to scale this up. So our perpendicular vector, our cross product here that's moving, is going to get longer as our edge segments get longer, and it's going to get shorter as they get shorter. But that's not the only thing that makes it longer and shorter. This is making it hard to see, so I'm going to turn that off, and we're just going to go into full view here. Okay, so see our cross product there. This is our cross product is getting shorter as our edge segments get shorter. It gets longer as the edge segments get longer. It also gets shorter depending on their angle to each other. So, like if they're close to being hiding this. If they're close to being exactly parallel to each other, like, let's see, we'll get them to where they're parallel. Oh, I moved the wrong one. I moved this guy, right? No, that is the right one. Yeah. So we get this to where these guys are parallel. Then our cross product keeps getting shorter the closer you are to parallel. And if you can get it to where they're exactly parallel, let's see how tiny our cross product is there. Like if I snap this guy over to here, now our cross product is going to have a length of 0, and it's gone. We're not printing it, but it's there. So there it starts to show up again. Starts to show up again, and the cross product is at its longest when these two vectors that we're getting the cross product from are perpendicular. They're at a 90-degree angle to each other. And it just so happens that the cross product is equal to the area of the parallelogram that would be described by these two edge segments. So a parallelogram would be like if I had these two edge segments and I made a shape like this out of it. So there's my parallelogram. This is a quad, and the area of this quad is equal to the length of the cross product. So you can use the cross product to calculate area, as well as using it to give you a vector that's perpendicular to two other vectors. Cross product is really cool. Now, because this cross product keeps changing length as these things are changing angles and stuff like that, that can be problematic depending on what you're doing. So what people generally do is convert the cross product to a unit vector. So let's just do that. Let's take our cross product up here. CO equals cross plus blah 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 blah. Okay, before we turn it into a unit vector, or actually before we add 0, we're going to do the unit vector thing. So let's see. To make it into a unit vector, we divide it by its length. And to get its length, we do cross. Actually, the first step is to get the square root. So we're going to do np.sqrt and cross at cross. And we can do it in place. So we can do cross divided equals np.square root cross at cross. We add the offset back to it so that it's, because it's just a vector starting at 0, 0, 0, we want that vector to start at CO0. Now this vector, this cross product is going to stay the same length because we've converted it into a unit vector. Provided I don't do something silly that prohibits it, like I just did. What did I do? Variable, oh, I spelled it wrong. Cruise. Alright, so now it's working correctly. Now, remember before I showed you that our cross product kept changing length. Well now, even if they're, I think if they're perpendicular it's going to freak out and it's going to be all nans and stuff, but even though these are getting longer, our cross product is staying the same length. So we're going to make these super short and our cross product stays there. It rotates with them, but it always stays the same length because it's now a unit cross product. Okay, that's about it for now. We'll do some fun stuff with this scene handler, frame handler type thing in our next tutorial. Hopefully I didn't overwhelm you with weird math and things. Hopefully you can think of more simple, fun stuff to do with the frame handler and scene handler. You could just like map the object location with the frame handler so the object moves around. You could play with sine and cosine and make your object like bob up and down on a sine wave, or whatever other stuff you can think of. You can do that with the scene handler and the frame handler. Until next time, thank you for watching, and I will not see you next time because I can't see you through the YouTube video, and you can't see me either. But we will hear each other. Actually, you will hear me in the next video. The end.